Okay, welcome back. It's time now to continue our series with the Raspberry Pi Model 2, getting some I2C devices hooked up. So what we're going to do is we're going to build this circuit up over here, Raspberry Pi Model 2 going through an isolator circuit, and then we're going to have a 4-channel digital to analog converter, a single channel digital to analog converter, both 16-bit, and then at the top we've got a 4-channel analog to digital converter, so we can read things back. Now that's all we're going to build on this particular video. What we're going to do on the next one is we're going to do some SPI devices as well, and maybe look at some GPIO handling as well, which is pretty basic stuff for the GPIO, so I'm not really too worried about covering that right off the bat. But with the SPI, all of these things are going to have different addresses, and so they can all share the 2-wire bus, which is really nice, because the only thing that's going to come out of the Pi for this to work is we've got a power plus and minus, so 0 volts and plus 3.3 volts coming out of the Pi. We've got the I2C, SDA, and SCL, which is the clock and the data lines. Now the isolator which we've got in here, this one down here, this is a Texas Instruments chip that I've got, and the part number is ISO1541. And what this is it's an isolation barrier for I2C devices specifically, and it provides in excess of 1,000 volts of isolation between one side of the device and the other. Now of course, if you're building that onto a PCB or something like that, and you want to be able to actually have that amount of voltage isolation between them, then you need to take extra precaution with your PCB too. For instance, having a complete trench cut in the PCB right through. So you would cut a slot right down the middle of the IC underneath it where it's going to sit, so that you've got this increased resistance to arcing and bridging of the circuit. I can't remember the exact names off the top of my head, but Dave Jones on the EEV blog has done a lot of articles and posts in the past all about isolation and everything else as far as PCB layouts and what techniques for safety and everything. What I'm doing this for is, in the power supply project that I'm doing, I want to be able to have 2 or more power control systems, so 2 channels of voltage and current control for the power supply, and potentially a DC load and maybe a constant current source or something like that as well. But all of these things, I want to have them isolated from each other using separate transformers and power supplies, so that they can be configured in series, in parallel. One can be a load, and one can be a source for power, and all sorts of things like that, and I can use them independently without worrying about the grounds conflicting and constraining what I can do. Now the one way of doing that is you can use optical isolators and things like that to do the isolation, which is great, but they have certain speed limitations. These particular chips from Texas Instruments, and you can get them from other places as well, they provide high voltage isolation, but they still allow you to run at the proper I2C communication speeds and everything else as well. And the other benefit is, you know right off the bat that they've got the high voltage isolation because they're certified for it, and they're tested for it, but also that they're specifically designed for working with an I2C bus. And I haven't got them yet, but I'm also getting a hold of some for the SPI bus as well. Obviously they have more lines on them because I2C is 2-wire and SPI has 4 wires if you include the chip select. And once they come, I'll do a video for the SPI and cover that off as well. But the basic technique is the same. The Texas Instruments chip have a capacitive barrier between one side and the other, and all the circuitry inside the chip, which I don't know what that exactly is, but it provides the isolation that we need. Anyway, I don't want to go too much into that right now, but what we've got in our case as well, the other benefit of this is that on the Raspberry Pi side, we're going to power that side of the isolator with 3.3 volts from the Raspberry Pi, but a lot of the circuitry that we're using on the ADC side and the DAC side, they will require at least 5 volts to operate. So we can power the isolated side of the barrier off of 5 volts and have that driving all of the SDA, SCL inputs, the I2C connections on all of those devices with full 5 volt logic levels. So not only does it provide us some great isolation from one side to the other, but it also provides us level shifting capability from 3.3 to 5 volts. And that all works perfectly well. So, and the other thing I'm going to do with this right now is the voltage reference I'm using is a 2.5 volt voltage reference. But if given enough time, I may drop in a 5 volt one as well to show you how that, with this exact same circuitry, just by changing your voltage reference, you can change the output range of your A to D and D to A, and the input range of your, you can change the input range of your analog to digital converters, and you can change the output range of your digital to analog converters. Now, the A to D converter I'm using here right now actually has a built-in voltage reference. It doesn't come outside of the package, but it also has a programmable gain amplifier in it, so you can actually divide the input volts down if you've got too high a voltage, or you can amplify them to a certain amount. And when we get to that one, we'll look at the data sheets and how to use it. Now, I haven't used this particular chip before, and I don't know whether there's any libraries already available in C or something like that to drive it, so it may be left to a subsequent video to start working with that one. I have done plenty of videos already with other A to D converters and things, including the 24-bit one, Sigma Delta ADC, as well as some 12-bit microchip ones, the 3208s and 3204s. It's a 2-channel and a 4-channel and an 8-channel ADC that are just 12 bits in resolution rather than 16. So it's all pretty much the same kind of deal. And in fact, if I can't figure out this one quick enough, I might just drop in one of those devices and see where we go. But there's, no, I can't. They're SPI devices. They're not I2C devices. I have very few I2C analog digital converters available to me right now. So we'll have to see how we go. But either way, we'll get the D to A converters working, and you'll see how the isolator works, and we'll see how well we can control these from the Raspberry Pi. So let's get to it. So with a better close-up of this picture and having it set down so that you can actually get to see it, what we've got is the 4 wires coming from the Raspberry Pi, the 3.3 volts, the SDA, the SCL, and the ground, going to 1/2 of this ISO 1541 chip. So you've got VCC1 and ground 1, which are of course the Pi side of the device with the SDA1 and SCL1, and then you've got the isolation barrier between the two, and this is inside the plastic of the chip. This is completely isolated from the left and right side of the chip, and all of the pins for one side are all on the same side of the 8-pin chip. All of the pins for the other side are of course right on the other side, so that allows you a lot of flexibility with your PCB design to keep things as far apart as possible. On the other side, you've got a VCC2, a ground 2, SDA2, and an SCL2. So both sides need pull-ups. You've discussed on previous videos the fact that I2C does need to have somewhere between sort of 1.5K, 10K pull-up to make it work properly, because they're typically open collector drivers and things like that. So in the case of this isolator, you need pull-ups on both sides of it, going to their respective rails. The other three things we've got here is a DAC 8574, which is the 4-channel 16-bit digital to analog converter. We have a DAC 8571, which is basically a single-channel version of the 8574. The difference on this one, though, is the 8571 has a sense output, which is, it's got a non-inverting op-amp on its output stage internally, and the negative feedback on the op-amp is actually brought outside, so that if you have your actual useful connection to where your load is a little bit away from the chip, you can actually take the sense wire right as close to the load as you can, so that it automatically compensates for any drops in the wiring and things like that. And the third chip is the one that we're going to add to this, which is an analog to digital converter. It's an ADS1115, 4-channel analog. It's got a comparator internally as well. I'm not sure if we'll get to try that out. It's got a built-in voltage reference, and it's also got a programmable gain amplifier. So I might just going to break into a quick video, quick cut in where I've just soldered up the chip onto a board. So this is the board here. I'll bring that in, see if it can make it focus on it. There we go. So you can see it's a tiny little 0.5 millimeter pitch IC. It's 10 pin, so I've got a little PCB header to allow me to plug it into the breadboard, and we're going to get that connected up now. So let's go to the breadboard and see what's involved. So in preparation for hooking up a bunch of I2C devices onto my Raspberry Pi, I wanted to have a I2C analog to digital converter as well. So what I have here is an ADS1115 from Texas Instruments. It's a quad 16-bit analog to digital converter, I2C bus connected. It can either do 4 individual channels or it can do 2 differential channels. So it's on a tiny little chip here, as you can see. I'm not going to put my macro lens on because I've shown you plenty of times before how do these things go. But this is a tiny little 0.5 millimeter pitch 10-pin IC, which is the chip that's in question, and I'm going to be soldering onto this little header board here. Now typically I end up putting way too much solder on these things, so I'm sure that today is going to be no different. But these little chips are actually quite resilient, and even though I'm heating them with my hot air blower, they actually are quite tolerant of me having to go back and rework them if I do end up with a bit too much solder on, and maybe some connections have gotten bridged or something like that. So anyway, I just figured that I would let you see how I do this. Now I'm going to speed up the video from this point on because like I say, it's all been done before and I just want to get this done, and just figured I'd show you a bit of the process. So tiny bit of solder at the end of my syringe here. Even the amount I've got here right now is way too much for this little board. But you know, it's how much you really nice to do on these things. So I'm just going to switch it a little bit on here. Switch it. This is already a tin board as well, so this is one I'll probably get flux on at the beginning. So as you can see, I've touched on that end of the syringe on the other side. I'm going to take my pliers here, my tweezers, and these things are actually orientation chips, and they have a little docking one corner, which is pin 1, and pin 1 on this board is just here, and the track actually comes up to here, which is pin 1 as well. So we're just going to drop this on, hit the line and sort it out just right, and then we'll heat up with my pocket gun to get the solder to reflow and make connections. That's pretty much all lined up there. I'm just going to rifle down a little bit so I can check and start getting away. That's it. There you go. Got the lights line quite nicely, so I'm going to organize what you just reflow more. And I'm just going to reflow this now. Okay, we get that down without getting away. I'm trying to make sure I don't blow it off. But then just move the thing doing this under the camera, which makes it a lot lopsided a little bit. Okay, nice. Get that now without blowing away. Okay, that side's already reflowing, as is that side. So it does have a little bit of a bridge on one side of that, so I'm going to have to take a little bit of solder wick and just suck off the excess. All in all though, not too bad. Let's just put that out of the way, heat up my other soldering iron. Yeah, so 2 tiny solder bridges. One is up in this upper right corner here. So let's just get this done, and then we can get the thing finished. So we just put a little bit of solder wick on the side. The soldering iron here will just quickly, we'll just do one side at a time. It'll suck it right off. That's done there. You don't want to leave this stuff on too long because it will lift tracks and heat the chip up a lot as well, but that looks like it should have done the job. If you just give me a second while I just look with the magnifier again. A little 10 times uphill view thing here. So yeah, that's good. Just check that side of the chip now, and that side is all good. So that's it. Now I just got to put the outer ones on, and then that'll be ready to go onto the breadboard. Okay, so here's the breadboard we're going to be using. This is the new chip, which is the ADS1115. I've just sat it on top at the moment, haven't plugged it in. And in case you're wondering, the wires here, the red and the black, these are 5 volts that are going across to another breadboard over here, which has the isolator on. This is the isolator chip we were talking about. And you can see on one side right here, all these connections right here, this is the side that's coming across to here, to our target breadboard. And then the other side of this chip with these wires here, they're going up to the Pi header, which then goes across to the Raspberry Pi. So this is providing complete isolation between one side and the other, and there are no other wires that are coming across here. Everything that's connected is just this side. And going back to the board here, zoom out just a little bit, what we've got is this wire is bringing 5 volts across from a USB power adapter that I've plugged into my little safety outlet, which we built on a previous video, so go check that out if you don't have one yourself. Provides some ground fault circuit protection. It's got a fuse on the side, and it's got a switch that allows you to turn all the power off right away. So actually, as we're going to be doing some wiring, I'm turning that off right now. Yeah, if you haven't got one of those and you're doing anything that's got mains and stuff like that, you might want to consider making one. And all the instructions for this one, for the Canadian version for Ontario, is on the website, along with all my other videos. So let's just get back to the main thing here now, and we'll get this wired up. Now, I apologize for the odd occasion of getting my arms in the way here, because I'm not going to be able to keep them out of it while we build this thing up. But I'll do what I can. So the first thing is we've got to push this onto the board. Now, my whole bench here, this blue background that you can see, is an anti-static mat that is providing static discharge. So I'm not worried about actually touching these chips and things while I'm on my bench, because it's all ESD protected. So I'm just going to push this down into the breadboard. It's going into my fingers more than the breadboard. There we go. Okay, so the other chips that are on here, by the way, just to give you a quick rundown if you haven't seen any of my previous videos, is this one here is the Ref 5020, which is the 2.048 volt voltage reference. The next one is a DAC 8574, which is the quad 16-bit digital to analog converter. And then the last one that's tucked in over the back here, behind these caps and everything, is the 8571, which is the single channel version, which has the feedback. This little loop here is actually the ones that are on the sense, looping the output back to the sense. And then the probes are just going to a couple of my multimeters so we can monitor the voltages when we start playing. On the back here, this green and blue loop is the I2C bus jumping from one to the other. The brown and orange wire here are going across to the output of the isolator chip. The caps and things are just to decouple the rails, because there's lots of clocks and square waves, well, not quite square waves, but almost square waves floating around, and we really don't want to have any glitches on the power causing issues with everything else. So there's a few caps and things thrown around the buses just to provide some decoupling and noise suppression. The voltage reference chip here right now is feeding one wire across to the single channel digital to analog converter, and another feed across to the quad channel D2A converter. Now, the IC that we're plugging in right now doesn't have an external voltage reference, so we won't be needing to make any connections to it, but we will need to connect up the I2C bus across to it though. So if I just grab some wires, now that the chip is plugged in, we've got the power disconnected, I can start running some additional cables. So I'm going to use this little jumper here. We're going to make a connection from the, let's have a look at the best place to pull this from. I got a header there that I'm just going to move out of the way, if I can get it out. Excuse for the blocking of the camera shot for a second. Okay, so we're going to put the black and white cable into here and drop it down right there. That gives us that connection to come up. Now I just got to check on the 8574 schematic. The 8574 pin 11 is SDA and pin 10 is the clock. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the black wire in this case is on pin 10, which is SCL, and on our new chip, which we're putting in, SCL is, well, it's also pin 10. That's kind of handy. But in this case, obviously, it's a completely different position because it's only a 10-pin chip. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to go to the top connection for this one, for the SCL, and in our case, pin 9 is the SDA, which is pin 7. Sorry. Which is pin 11 on the 8574, which is the next one up. So we're going to connect that from that one. Just going to flip them around, plug that in here. That's our I2C bus hooked in. Now, of course, we need to give it 5 volts and ground. So 5 volt connection is on pin 8. So let's just grab a little jumper here, and so that's pin 10, 9, 8. So the third one down here, we're just going to jumper across to 5 volts on the bus here, so we drop that in. There we go. That's 5 volts connected. Ground is on pin 3. We also want to connect pin 1, which is the external, it's called ADDR on this particular chip, but on the other D to A converters it's called A0, and what it allows you to do is offset the address on the SPI bus. So what we need to do is connect pin 1 and 3 to ground, so we're going to do that on the other side of the breadboard on this side. So we're just going to drop these jumpers in. So this one is the pin 1, we're going to connect it to ground. So that's done there. And then pin 3 is going to go the same way. Now that one doesn't align with a hole, so we'll have to do it at a slight angle to get that one in. So pin 3 there, and we're going to jump it across. So give me your fingers a second, and I just get this in. There we go, that's pin 3 connected to ground as well. Pin 2 is an output for alert, or when it's ready for after doing analog to digital conversion. So we haven't hooked that up onto any pins at the moment, so we'll just leave that open for now. It's an output on the chip anyway, so it's not going to harm. Pin 4, 5, 6, and 7, so these bottom 4 connectors around this edge, those are the analog to digital inputs. So what we might do with those in a minute is maybe hook them across to the quad digital to analog converter, so we can set some voltages coming out on the ADC and read them back in again. Sorry, set some voltage going out on the DAC and read them back in again on the ADC. So are there anything else we need to connect here? I think we've got pin 2, doesn't need to be connected. 4, 5, 6, 7 around the bottom are the inputs. Pin 8 is connected to V plus 5 volts. Pin 9 and 10 are the I2C, and pin 1 and 3 go to ground. That's pretty much everything connected, so we should be able to now power this thing back up again. And you've seen in previous videos where we've done a scan of the I2C bus, and it gives us a complete list of the port addresses. So if we do that, it's just going to get connected back in again. Okay, if you remember from the previous videos, the command we use to scan the I2C bus is you got to run it under root, so we do sudo, and then it's I2C detect, and then you specify -y so that it doesn't bother prompting you, and you specify the bus number. Now we already know that bus 1 is the one that all of these devices are connected to, so let's see what we get. Hopefully all the existing devices will show up. Now we should see 3 distinct devices when we run this one now, because we've got those the ADS1115 in, as well as the 8574 and the 8571. So I2C detect, and we'll say -y for yes, don't bother prompting me and give me any warnings about scanning the bus, and we'll tell it to do bus 1, and we'll press enter, and we only get the 3 devices. There's actually 3 devices being shown here, but we actually should be seeing 4. This address 48 is actually a common address for these two. The 4C is the 8571 and the 4D is the 8574. But remember I said earlier that you can actually address them as a group, and the 48 is actually that common address for these other ones. So I'm going to have to see why this other device here is not actually giving us any responses. So just give me a minute while I just figure out what's going on with it. I've never used one of these before, so it could be something simple, but we'll get back to it. So note to self, and for any newcomers out there alike, pay attention to the data sheets. The default address for the ADS1115 happens to be the exact same address as the base address of the DAC 8574 and the 8571. So of course it was already showing up as 48. There was no way that it could actually distinguish itself. So what I've done is I've taken pin 1 and I've connected it to V plus instead of ground, and what that's done is it's bumped it up by one address location. So now it shows up as address 49. So now you can see here we've got 48, 49, 4C, and 4D. So there's our 3 devices with our 4 addresses. So that's a good start to everything. Sorry about that little bit of confusion there. As I say, it's I should have read the data sheet. I just assumed that because it was a different family, it would have been on a different address. But luck would have it, no, it's not. So let's now look at what we can do with these things. All right, so what I've done here is I've pulled up some documentation I had a while ago for using the I2C bus on a Atmel SAM5D4 board, which is another embedded Linux system. And basically, once you get in Linux and you're using I2C, how you actually use these is pretty much the same. So we're not going to be using Gordon Henderson's library just yet. We'll get to that in a little bit. But what I want to do is right now is basically show how you can set things like analog outputs and things on the 2 DACs that I have that I already know how to talk to. So the way you do that with these things, the I2C commands that are built into Linux when you've got it all enabled, which we now do have, is you can actually do an I2C get and you can do an I2C set. All right, and the differences are that the I2C get is reading data from a chip, and that's something obviously we would need for the analog to digital converter, and the I2C set is actually for writing to a chip. And there's different ways of doing it. You can do byte-wise and you can do word-wise writing. Now, because this is a 16-bit digital to analog converter on these things, we obviously need to do word writing. So what we're going to do is we're going to do an I2C set -y to confirm, because if you don't put the -y in, it always prompts you to say, you sure you really want to write to this device and all that kind of stuff. The 0 is the bus number, so of course on SAM5D4 it is on bus 0 for that instance of Linux. In our case that's going to be bus 1, so we're going to change that to a 1, and the address, I happen to be using the same chips when I was doing that demo, so it's using the same 48. Now I'm going to show you something about that, so I'm going to leave it with 48 right now, and then I'm going to output FFFF, which is the maximum value for the D2A converter. So if you remember what I said, my voltage reference should be about 2.048 volts. I haven't tried trimming the voltage reference or anything like that, but it should be roughly that, give or take less than 1% or something, and we'll see what we get. So let me just power up my 2 meters. I've got one connected to each of the ADCs. And I think what I might do is also hook one up to, well, I'll just use my other meter that's here and hook that. I'll just probe the voltage reference to just confirm what it's sitting at right now. It should be 2048 if I've wired everything up properly. So let's just go across to my meters here. So you can see the U1461 here is hooked up. Let me just trace the wires through. Is hooked up to output 1 of the quad D to A converter. The U1273A is hooked up to the output of the 8571, the single channel D to A converter. And this one here, I'm just going to use it to probe the VREF output just so we can just confirm what it's sitting at. So I'm just going to connect one wire to ground there and connect to the voltage reference output of it and see what it reads. There. So 2.042. So should be 2.048 ideally. If I just change my ground point, it might be because of, breadboards are notoriously bad for creating noise and things like that. So if I just change things around and find the ground point, I think that's it there. 0.047767. So that's good. All right. So when we get our output set up, we should see very, very close to that. Now obviously with gains not being set right and things like that, you would normally just adjust the in software any errors. So ADCs, sorry, digital to analog converters, they don't have to be ultra accurate these days, as long as they will actually get the range that you need and that they're fairly linear. You can compensate for any errors in the outputs in software. So if you know that if you output FFFF and you're slightly getting more than what you want to get, then you can actually in software say, well, when I want to get the full voltage out, I'll actually output something like FFFC or something like that instead. So I'm just going to go back to the terminal connection here, and I'm going to just edit the line, so it's going to 48, and I'm going to change that to bus 1. Now remember what I said before, that port 48 on the I2C bus for these chips, they all communicate on the same one, on that base port. So if I tell one of them to output on FFFF on its channel 1 out, we're probably going to see both of these actually do it. So let's see. Let's just hit enter, and yep, the first one, they've both gone to 2.044 and 2.053. So they're both slightly different in their linearity, but nevertheless, as you can see, they've both gone up at the same time. That's because they're using that common bus. Now what you would normally do with this, by the way, is you can write to each individual chip using their other addresses, and then but write to it in a way that sets up temporary registers inside the digital to analog converters, and then you can go to the base address and send one command out that actually can address many chips all in one go to say, okay, now transfer your temporary register out to your actual output and turn it on, or adjust it to whatever you set. That way it allows you to synchronize all of the outputs to different voltages at exactly the same time, rather than output 1, have it adjust, and then you've got delay with your software while you go and set up the next one and turn it on and then go to the next one. It allows you to set them all up at the same time and then just issue one command to the base address that allows you to do everything. So what I'm going to now do now is I'm going to, if I get my addressing correct, I'm going to send a command out to 4D, which should be the 4-channel one, which is the one that is connected to this meter here, and I'm going to tell it to output 50% of the voltages. Now it actually has to output 0080, not 8000, because of the order that it sends the bytes out to the I2C bus. It sends the low first and then the high, versus the high then the low. So I'm going to send it right now. And there it's gone down to 1028, which is roughly half scale. And if I now talk to the other one on its own, which is on port 4C, change that to C, and I'll make that one 4. So it should be a roughly 0.51 volts, sort of. Yeah, roughly that. So there we go. The U1273A multimeter is a little slower to jump to new readings. So there you go. So now I've managed to individually address those two and set their outputs. So the next thing, I guess, to look at is how do we get this ADS1115 to start working. So let me just do a quick check on the internet and see if anybody's actually done this already, and maybe save myself a little bit of time. So let me get right back to you. Okay, figured out how to make this thing work. The ADS1115 has a number of registers inside it, and in order to get to them you have to write a value to a pointer register. Only the least significant 2 bits are relevant because the chip only has 4 registers in it. The reading register, which is register 0, is obviously read-only, and it reads out the 16 bits from the results of a conversion. And the register 1 is a configuration register, which is read-write, and what it's got is a number of bits that actually control the operation of the chip. So the ones that we're actually interested in, because we're just going to use one of the channels right now, is the OS bit, which is the operational status single shot conversion start. So if you're in single shot mode and you write a 1 to D15, that means it'll actually initiate a conversion for you. And if you're in continuous mode, then it gives you the status of the conversion, so it'll be a 1 or a 0. The next one that we actually need that is of interest, of course, is the MUX registers. And what these do are they will configure which channel you're listening to converting from, and whether you're in differential or single-ended mode. So if I just scroll down a little bit a second, we'll have to go back up that in a minute. So here are the MUX registers, all right? So if you have 000, which is the default behavior, then you're actually running in a differential mode where analog 0 is the positive input and analog 1 is the negative input. What we want to do for the sake of our test here is actually run with 100 as the selection, which makes analog input 0 the positive and analog input and ground as the analog input negative. So what we're doing is it's basically a 0 offset. Now we can run in differential mode, but just for now we're just going to run in single-ended mode. So to build this up, what we're going to have is the very most significant bit is going to be a 1, which means that's at least 8000 that we're going to output. Now the next bit that we want, remember, is going to be the 100. So that means we've got an 8 and a 4. So now we're at C000 that we need to output at least. All right. Now if we work down these, we've got a programmable gain amplifier here, which now that we've gone past the first nibble, we're now into the lower 4 bits right down to bit 8. So what we have is a 2048 voltage reference right now, so the outputs are not going to exceed that, which is the default behavior. So we actually want to, and we also, to make that happen, we want to have a 010. So that's so we want to add a 4 to it. So we've got a C, and then we want to have a 4. So we've got a C400 right now, and then we want to set the operating mode. Now remember, we said that we're going to run in a single shot mode for now, where we just send a command, make it do the conversion, and get the data out. So we've got a C4, and then with the least significant bit set as well, we need to output a C5. If we wanted to run in continuous mode, then we just output C4, and you'll be able to just go read, and you should get data coming back. And if you vary the input, you would see that, but we're just going to run it in single shot mode. The next set of bits are for setting the samples per second and the comparator windows and stuff like that, the way the comparator works. So we're not using the comparator for this experiment that we're doing right now, and the data rate really is irrelevant as well because we're doing it in single shot mode. So what we're going to do is we're going to output 0 for the conversion data rate, which is basically 8 samples per second. The next few bits don't really matter, and then when we go down to the least significant bit of the second byte, we want to disable the comparator, which means we want to output 11. So what we now have here is a C5 as the high byte that we want to output, and a 03 as the low byte. Now if you remember what we were talking about before, we actually output the high byte last, so we'll actually do a write to the analog to digital converter of 03C5. So, and then we'll read back from register 0, which is the I2C get, and we'll specify register 0 instead of register 1, which is the config register, and read the data back, and we'll see what we get. So if we go back to the screen right now, all right, I've already been playing with this just to verify what I was saying. So what we need to do to get the conversion to start is here, where we have an I2 set. Can you see that on the, no you can't, sorry. All right, so what we're going to do here is an I2 set -y for just don't bother prompting me. We want to tell it that we're using I2C bus 1. We're going to output to register 49, which is what we've configured for the I2C device. And the first byte that we output is the control register, so we're outputting 01, which tells it to write a 1 to that first control register, and that says that the next 2 bytes are going to go to the configuration register, and this is where we output the 03, which basically disables the comparator, and then the C5, which triggers a start of conversion. It sets it to be single-ended input on A0, and the 5, the least significant bit, says to make it a single shot conversion. All right, so we're going to start the conversion. We're picking register input 0, and we're initiating the conversion. So that's what we need to do there. So we just output that, and that basically is now fired off. We didn't get any errors because, well, it really doesn't answer us back. And now we need to read from the ADC to see what we've got. So if I go to I2C get, basically the same structure, except in this case we're doing a get instead of a set. We're going to read from 0 this time because we actually it's the conversion register we're going to read from, and the W at the end says we're going to read a word. So if we actually read that in now, you can see here what we've got is basically 3EF7 is what we're reading. Now if I just turn these meters on again a second, we'll read what we've actually got coming out of the device. So I've actually got a 1 volt, so that's anyway, it's what I've done is I've sent the output of DAC register 0 to the input of the ADC register 0, and I'm telling it to read that voltage. So if I go and output a full range on the DAC, so FFFF, that's going to set it up to 2.048, where it's actually reading 2.054. Now if I go do that conversion again, all right, so output the C5 for the conversion, and we'll now do the get, which is this one. We should see, all right, and what it's doing here is it's giving us 7FFF, which is basically full scale. Now the one thing I found out about this chip is that it is not basically it's not really 16-bit. It says it is, but it actually does plus and minus. So even though it won't go negative, because it's got the differential inputs, we've basically tied one to ground and the other one we're going to take up and down. So it's losing a bit, which is this most significant bit, which is the sign bit. So it's really actually doing a plus and minus 2.048 volts. So it's lost one piece of resolution, which is why it's only showing us the where is it, the 7FFF reading, even though we had outputted FFFF for the same thing. As I said, lost the most significant bit. So now if I go back here and I output, let's go output half range, so 0080, that's output on the ADC, and my meter now says 1029. And now if I go and do the reading from the ADC, and I'm just doing this in hex right now, so of course it's you know, I'm doing conversions in my head, so that should be roughly 3FFF if it was following suit. And this, you know, it's 1024 is what it should be coming out of the DAC, and it's actually slightly high, and this is reflected in that as well, where I've actually got 4030. Now remember, we're reading this backwards. It actually says 0x 3040, but the 40 is the most significant byte, sorry, and the 30 is the least significant byte. So it's showing us there that it's reading roughly the 1 volt. Now if I now go and output, let's see, change it down to 4, which is half that again. So what I expect to get is probably a 1FFF or a, you know, 20 something. So let's just output that, and we'll do the read again. We'll trigger the conversion, and we'll now do the read. And there it is, 202F. So it's reading just a little bit high, but it is definitely reading. So yeah, there we go. We've actually managed to get this thing to read properly. Now, if we want to change the gain of this, of course, because it is only reading, you know, it's differential inputs and things, but you've got a programmable gain amplifier on it. If we go back to the data sheet here, we're running right now with a programmable gain of where is it, 2048 volts input, which is the 010, which is where we have the 5 set instead of just a 1. We can actually change this up or down. So if we made it a 6, 1, sorry, 5, 6, 7. So this is bit 1, this is bit 2, which is the least significant bit of the gain amplifier. So if I actually output a C7 instead of a C5, then what it's going to do is it's going to make the maximum range of the ADC 1.024 volts, which will give us more accuracy at that low end. And we can actually go down all the way down to having 0.256 volts. So if you're actually using, say, a current shunt and you're in the low milliamps range, and maybe you've picked a shunt that's capable of handling up to 10 amps. So of course at 10 amps you might have maybe a couple of hundred millivolts so coming into it. So you want to have a gain that would be is there a gain on here? I get you would reduce your sensitivity down to the 111, which would give you an input sensitivity of 256 volts, 256 millivolts, which would then allow you to see the full range. Now, if you were on a much higher, sorry, I got that description slightly wrong, I think. If you had a shunt that was, just for argument's sake, it gave you 1 volt, or let's make it easy, we'll say 2 volts at 20 amps. All right, then you would be picking the one that we're using right now, which is 2.048 volts full scale, so that you could read the high end of that, which when you've got your 20 amps flowing through. But if you then reduce that current down to, say, instead of 20 amps for 2 volts, you go down to 2 amps, which is going to give you 0.2 volts on your input, then you could actually bump your full scale down to 256 millivolts, which would then allow you to still sample with maximum resolution, even though you're running at only 10% of your input. And that allows you then, if you went down even further to say 200 milliamps, you would still have some decent amount of resolution for making your readings. Now, this actually doesn't have it's called a programmable gain amplifier, but it really isn't making a gain, because it's got, it's basically picking different full-scale inputs. It's not allowing you to actually amplify your input signal at all. It's just effectively changing your VREF internally. I mean, it technically is doing a gain, because I think if you look at the actual spec, it's like down to an 1/8 and things like that with an amplifier down at this low end. Your default of 2048, that's probably where the actual internal voltage reference is 2.048 volts. So these top two is probably a divide by 2 and a divide by 2/3 or something like that up the top here. And at the bottom end is probably starting to do times 2, times 4, times 8, times 16, and times 32 or something like that as you're going up on the other side. We could probably have a look at the data sheet to figure that out properly, but you can do that yourselves. Suffice to say that if we just change this right now to be C7 instead of C5, we actually should be able to see much more of this lower end. So I've only got a low output coming out right now. So if we do this, I outputted 4.0, which is only the 0.5 volts. So if I do a conversion with C7 instead of C5, instead of getting 2.0, now we probably should get twice that, which would give us something around the 4.0 value, because we've now told it to do the times 2, and there it is, 405E. So we've actually changed the gain now. Now we can go one step further probably and actually even have something lower. So we've got 011, which is the 7. If we go up to a 1/2 volt, which is probably going to take it to full scale this time, because we're sitting at 5146 volts coming out of this thing, which is 100, which is C8 now. Instead of 7, we're going to output C8 plus the 1, which means we're going to output C9. All right, that actually then should give us a range that is way, way higher. C7, C8, C9. Now if we do this and we read, we should get a value of, whoops, instead of 4.0 something, it probably is going to be 7F-ish range. So let's go and do a reading and get that back, and there it is, 7FFF. So it's basically gone slightly over full scale, so it's actually maxed out at 7FFF. So you can see very, very easily, just from the command line, we've been able to study the data sheet and figure out how to use the ADS1115 from the command line. Now it's just a simple case of integrating that into Python or any other program you want. I've already shown you talking to the 2 different digital to analog converters, and in previous videos with the Pi B+, not the Pi 2, I've shown you how to talk to a port expander and things like that. So I think that's going to be it for now for this one, for the I2C. I will start putting together some additional libraries and documentation for other devices, because I will be using this as part of my power supply project documentation and experimentation, because I've got, with the Raspberry Pi, I can do full GUI interfaces and everything else for it. In the next video, we're going to look at using SPI devices, very, very similar with the isolation chip and everything else. So I hope you like this one. Give me a thumbs up if you do. It helps on my ratings and everything else. And I'll see you for the next one. I'll be posting all of the circuit diagrams and everything online, and I'll link to it in the YouTube post as well. Thanks. Bye.